Hey guys, today we're looking at STAR-CCM by Siemens for beginners. This is a very bare bone initial introduction to STAR-CCM, and we'll be covering setting up, meshing, running, and getting reports and coefficient pressure gradients for a simple car CAD geometry. STAR-CCM is mainly used in a variety of industries like automotive and aerospace, and essentially models computational fluid dynamics, CFD. So it's a physics model, a physics simulation. By feeding your CAD design to the domain or the 3D space and then setting up the respective physics properties, meshing, then setting up the reports, monitors, plots, and scenes, we're able to see approximations of how your design will react to specific physics environments. This will help you pinpoint areas of improvement, where your design is weak, where it is strong, and can help you formulate new solutions, rerun, and reiterate to yield better, stronger, and more efficient designs for your engineering projects. So first, you want to go in the upper left corner and select File, New, and create a new file. I already have a saved configuration that pulls up my license and key and all the information I need for my STAR-CCM to run and create a new file. So if you haven't done this already, make sure you set up your respective key, your respective license, and make sure to save that so that you don't have to retype it every single time. Once you have that pulled up, simply select OK to create that new file. Next, we're going to import our respective car geometries. I pulled a simple CAD geometry from a free database online, but if you have your own design, feel free to pull that in by simply selecting File, Import, and then Import Surface Mesh, and then simply select your part from your file location, and then select Open. Another window called Import Surface Options will pop up. For this window, I just keep the default and select OK. Next, you will see that your car or your design will pop up in the default geometry scene 1. That pops up when a file is created. In here, you can see the car under Parts. Now, there are two sort of main subsections under Geometry folder. One is the 3D CAD models, and the other one is Parts folder, as we can see here. The 3D CAD model is more of that physical CAD that you can go into and edit, and then the part is the part that gets uploaded into this STAR-CCM domain. And this is uneditable from the Parts folder. So if you do want to make a change, you have to go into that 3D CAD model folder, edit the part from there, and from there, the changes have to be updated so that the changes are then applied downward to the rest of the folders, such as the parts folder. Now here, if we look at the parts folder, we can see our geometry called car. You can rename this by simply selecting the part, clicking on it once, or you can simply right-click it and select rename. I like having fun with my projects, so I'm naming it to a silly name like Le Car, which doesn't make much sense. If you really want to speak French, it would be Le Voiture, but Le Car is more fun, so I'm keeping the name. Next, we want to create a domain. So this is essentially a rectangular prism that we're going to create, and it's going to encompass the car. And this is going to represent our wind tunnel for our specific environment that we want to test this car in. So to create this, as we mentioned, we're going to create a rectangular prism. So select that 3D model folder and create a part by right-clicking it and selecting new. Once we're in this 3D CAD space, we're now able to start creating that 3D prism. So go down to that toolbar at the bottom and select that icon that looks like a pencil, and then hit Create Sketch, located on the top right. Once you're in sketch mode, select the XY plane, which is essentially your base, the base of your wind tunnel or the base of your domain, and select Create a Sketch. Next, we're going to create that rectangle, so that 2D sketching for right now, and you want to select that third icon from the top, from left to right. It's going to be that 2-point rectangle, and drop your first point, drag it, and drop your second point. Now, ideally, when you're running a wind tunnel with, say, for example, a company, or if you're replicating this test on an actual wind tunnel, you want to make sure you have the correct specifications of not just the specific wind tunnel, but where exactly your car is going to be located within that domain. So make sure that you're very precise if you are replicating this, but for not overcomplicating things and keeping things basic for now, for this basic intro video, we're not going to worry too much about those specs. We want to make sure that, yes, this domain is symmetric and that the car is in the center widthwise and located a little bit more towards the front or more towards the inlet, but apart from that, fairly symmetrical about the X and Y plane. And now we want to move on to giving this some depth. So select Sketch 1 from the features tree and right-click it, and then select Extrude. This will give it some depth and create that rectangular prism that we're looking for. So now that I have this sort of prism, I'm going back into my STAR-CCM domain and getting the dimensions of the car so that I can create a domain according to the dimensions. If we look at the very top, you're going to see the toolbar, and you're going to see a tool that looks like a ruler. This is essentially for measuring. So this is going to be your tool to measure how tall, how wide, and how long your car is. But before you start measuring, you want to make sure you're oriented correctly. So you want to make sure you're oriented facing the front. So you want to do this by going into the icon that looks like a camera, and this will yield the respective views. If you go into the camera and you go into standard views and then select whether it's right, left, top, bottom, front, or back view that you want to measure from. Next, grab your ruler from that toolbar ribbon and measure the height of the car to yield a rough measurement of how tall it is. You then want to repeat this for the side to see how long the car is and also to see how wide the car is. And also double check your measurements to see that the height is correct and that the width is correct and that all other measurements are correct. Finally, we want to go back into our 3D CAD geometry and give that prism some more accurate measurements. Next, we want to create this domain. So create that new 3D CAD model and create that domain and then give it rough measurements. So the rectangular prism is larger than your car's length, width, and height by X amount. Now the amount that you want to make it bigger than your car will depend on you and will depend on your wind tunnel, but I'm essentially giving my car a rough estimation of placing the car closer to the inlet, making sure it is symmetric about the width, and that lengthwise it is a little bit closer to the inlet. Everything else should essentially be symmetric, except for obviously the height. It should not be floating. It should be on the bottom, on the ground essentially. So you can essentially play around with that a little bit and see what kind of looks good to you and what makes sense. You can play around with the length on the length bar that comes up. And if you keep making updates to that 3D CAD model, just simply keep on selecting that update 3D CAD. Make sure you select update so that the changes do go through and that they update and that you're not working with an older version. Finally, when you're done making your changes, select close CAD instead of selecting update. So select update and then select close CAD. Next, you'll realize that you won't really be able to see your model yet on your STAR-CCM domain. You only see the part on the 3D CAD model. So you have to create the actual part for you to actually see that domain in the geometry scene. So keep in mind that the geometry scene only shows the actual parts that are in that parts folder. It won't show the 3D CAD models. So to make sure that this domain, that this prism will be shown in the geometry scene, you have to create a part for it. So right click the 3D CAD model that you just created and then select create new geometry part. A pop-up window with specific options will come up. I usually keep this as default for very simple CAD parts, but as you advance to more complex design, you can play around with this and change its properties to fit your specific meshing needs or any other refinement needs. But for now, I'm just selecting OK. Next, you will see that a new part is created under parts called the default body 1. Here, if we click on it, we see that the domain is displayed in the geometry scene and that indeed it does encompass our car. However, I wanted the car to be a little bit closer to the inlet and to be a little bit skewed closer to the inlet, and here it looks a little bit too symmetrical lengthwise. So I'm going back into my 3D CAD geometry and adjusting that. I'm then updating it and updating the CAD so that the changes are seen on the geometry and that the part is changed as well as the 3D model. You can keep going back and reiterating, but as I mentioned, if you are working with a real-time wind tunnel and you have actual measurements, make sure you use this so that it is very accurate to what you will be seeing in your specific wind tunnel scenario in real life. Finally, I generated a domain that I was proud of and that I was content with, and this is essentially a domain that would allow for a long wake to be taken into account with a good amount of inlet flow before it hits the car. Also, a domain that was tall enough to encompass any other kind of wake that might go a little bit further up. So essentially in the domain, you just want to make sure that you are taking into account all of the physics that you want to see in your simulation while making sure that you're being computationally efficient and that the sim doesn't have to run for longer than it really needs to by adding on unnecessary geometry. You will then mesh and which the computer will then have to run and iterate through, yield those solutions for you. So you want a good balance between giving your car that ample domain and space it needs to really give you accurate results, while at the same time not giving it too big of a domain that it will be computationally exhausting for the solver to iterate through and will increase that computational cost. Now moving on to the next step, which will be split by patch. Here we want to split the domain into each of its respective parts. So for the simulation, to recognize that there will be air flowing into this domain and then air flowing out of the domain, and then there's also its respective walls and a ground and essentially base, we need to split the domain or this rectangular prism that we have created into its respective parts. So its respective front, back, left, right, top, bottom. And then from there, we'll give it its function. So for example, the left, the right, and the top will just be very simple walls. They don't really have a very specific function, so we just keep it as a wall. But the front will be the inlet. This is where our airflow will be coming in through. If this were a wind tunnel, this is where the flow is coming into. And then the back is going to be our outlet. So this is where the airflow is coming out of. And then the bottom is going to be that base, that ground that that car is going to be sitting on. So if you open up that domain part within the parts folder, you're going to see another subfolder called surfaces, and then one singular surface called default. What this is telling you is that there is one single surface that is being defined right now. So the entire domain, the entire rectangular prism is being seen essentially as one single surface. So we want to make sure that we create separate surfaces for it so that we can give it specific roles. So right click this surface and select split by patch. This will then take us into the split part surface by patch, which the surface will then be numbered as we can see here. So you can start selecting the surfaces that you want to start creating. So for example, if you want to create a wall, like how I'm doing here, select that wall, that left wall, and that is the ID 106, and then select create at the bottom to create this surface, this new surface. So this new surface is created. So essentially what we've done here is we've created one surface, which will be separate from this default rectangular prism. So right now we have a total of 2 surfaces under that surface folder. And now you want to replicate this for all the rest of the other surfaces. Once you're done, select close and then rename your surfaces so that you can keep track of and remember which surface is which. Next, we want to identify the area that this mass flow will be flowing through. So we want to identify the car within the domain. What we're going to do here is create a Boolean, a subtract Boolean, because right now we only have the car by itself and the domain by itself. We don't really have the combination of the domain and the car. So the domain essentially just has a mass flowing through it that we will set up in a bit. But this mass, if we just set it up and we just hit run, would not recognize the car that we have set up here. So we have to create a combination where the car is identified with this domain, and thus we have to create a subtract Boolean. So within the parts folder, select the domain, hold down Control, and then select le car or your car. Next, you're going to right click and then go down to Boolean, select Boolean, and then select subtract, the subtract Boolean. This will pull up this next window that says subtract parts. The target part will be the domain. So this is correct. This is the part that you want to subtract from. So you're going to want to subtract this car out of the domain. And a completely new part called subtract will be created. Another way to do this is by going into operations, which is also where you will be meshing your car, and right clicking operations folder, selecting new, selecting Boolean, and then selecting subtract. 2 parts that you'll be working with. So that's domain and the car, and then the target part, which is the domain, as we talked about. So since I've shown you how to do this using the operations folder, I'm just going to delete the subtract part that I created and keep the operations subtract that I created. So here I'm just going into that subtract part, right clicking and deleting, and then right clicking subtract under operations and then selecting mesh. Next, we want to set up our physics. So under continua, there's going to be a subpart called subfolder called physics or physics 1. So we're going to right click this and select models. So we're going to select the following models. So again, the scenario that we're modeling is that we're setting up a STAR-CCM sim for a medium level flow. This is assuming standard turbulent, steady state, and compressible flow. First, we obviously want to start by selecting the three-dimensional space, since this is obviously being simulated in 3D. Next, the material that we're working with is air or gas, so air at standard density and viscosity. Next, the type of flow that we're working with is segregated flow or standard solver, which defines the solution algorithm. Then for the equation of state, that's going to be a constant density, which is good for low speed or subsonic airflow. For the time, we're going to select steady, which assumes flow features are essentially constant over time, but for more features on vortices or wakes, choose transient. Next, we're going to choose turbulent, which is required for a high Reynolds number like aerodynamics. This activates the Reynolds average Navier-Stokes RANS solver. And then the turbulence model that we're going to be working with is K omega SST, which is good for high quality near wall and separation prediction. This is crucial for drag and lift calculations and solves turbulent flow field around the car. Another addition that we see on this right side is the all Y plus wall treatment, and this essentially defines how the solver calculates flow near walls. And that's the full setup of our physics. So we want to go ahead and hit close. Next, we want to assign the parts we created, such as the domain parts, to a region, and they will all come in as boundary condition parts, so you will have to change them to their respective function. So for example, changing an inlet from wall to inlet. So in the regions folder, you want to right click it and select new, create that new region. And then under region, you want to open up that boundaries folder to see your boundaries. We can see that there's only a default boundary right here, so we obviously haven't assigned our boundaries yet. So we want to go back into our parts and do that. So to do that, right click subtract under parts and select assign parts to regions. Next, this window is going to pop up, assign parts to regions. And so from here, you want to go to the bottom and select assign all parts to an existing region. And then from here, you want to click select and the region that you just created. You want to select that region. Then on the input box below that, you're going to select the create a boundary for each part surface so that there's a boundary for each of the surfaces. For example, there's a boundary for bottom, there's another boundary for inlet, there's another one for left, and so on and so forth. So each of the surfaces have their respective boundaries. So as we see here, we have all of the created boundaries, and now we want to go into them, right click it, and then edit the actual function of the boundary so that they're not all walls. Right now, they're all essentially walls. We want to change this so that the inlet is actually an inlet and the outlet is actually an outlet. So to do this, you want to edit the boundary. You want to click on the boundary, right click it, and then select edit. And then under type, make sure that the inlet is the inlet and the outlet is the outlet. Within your inlet, you want to make sure you open that up and make sure that the boundary specifications are accurate. So make that either a mass flow inlet or a velocity inlet. In my case, I'm simply doing a velocity inlet since it's easier to specify a velocity magnitude for a wind tunnel. And I'm specifying a simple velocity inlet value for the front face, which will be about 20 meters per second for a medium airflow. You also want to make sure that the direction vector is at 1, 0, 0. So this is where the airflow is coming from in the x direction, and then set turbulent input values here too. Next, for the outlet, which will be the back face, the pressure outlet, the gauge pressure is 0 pascals or ambient pressure. And we want to make sure that this is a no slip condition. So setting shear stress to no slip condition, this no slip condition essentially models the behavior of fluids near boundaries more accurately. Next, you want to create an automated mesh from your subtracted part by right clicking on operations, selecting new, selecting mesh, and then selecting automated mesh. From here, select the subtracted part, and then under select meshers, select surface remesher, which is essential for a complex car like a car body. Then select trimmed cell mesher. This is good for efficiency and alignment with flow direction. And finally, select the prism layer mesher, which is crucial for accurately resolving the boundary layers and capturing that drag lift forces. Then select OK. Then open up the default controls folder. Click on the base size, and you want this base size to be about 10 to 20% of the car's length. So again, if you don't remember, just go back and get that measurement from the views and the ruler tool, and then apply that base size. Next, we want to create a volume controller refinement. So we want to get those solid numbers for our actual design. So we want to get finer, higher accuracy around our actual design or our actual model. So we want to create smaller localized refinement regions near or around the car and for the wake region, which we won't be doing now in this basic tutorial, but it would be the next step. And this essentially would be downstream behind the car to get that wake region. So to do this, create a tight box around the car body. So the target volume size or target surface size to be about 5 to 10% of the global base size. So to start creating this volumetric control, we want to select that parts folder, right click it, select new shape part, then select a block. This will automatically give you the volume around the car. And from here, you can adjust the dimensions. And then once you have that, select create and close. Here you see we have the block volume. From here, you can do what we did before. You can simply click it and rename it. So I just named it to Le Car Vol. So under automated mesh, under custom controls, you see that we now have a volumetric control. This is how to create another volumetric control for a wake region. And to simply create a wake region, you can either be very accurate about it by creating actual dimensions, or you can move around the essentially blue dots or blue what look like atoms from chemistry that you can move around. So for now, I'm just eyeing it, but I recommend that you get highly accurate if you are working with an actual wake region. And then do the same as you did before and rename it to your respective name. For now, I just named it wake. And then go into volumetric control, right click it to edit it, and then go into the parts and select your two volumes that you want to specify as your volumetric controls, which is the wake and the region around the car. And you now have your specific volumetric controls that you can create finer mesh around so that it yields higher accuracy and so that you're more efficient with your computation. So these volumetric controls will be essentially refinements, and we want to create smaller localized refinement regions, so near or around the car and for the wake region, these two volumetric controls. Target volume size or target surface size is going to be 5 to 10% of the global base size. For the wake refinement, this is going to be the long block starting just behind the car and extending to the outer boundary, so tall enough to capture the full wake height. Target volume size is going to be 10 to 20% of your global base size. This resolves the turbulent energy dissipation and pressure recovery in the wake, and this directly affects the coefficient of drag. So again, make sure your wake region and your car box volumetric control are specific to your scenario, and you're able to get your own measurements and know your own specifications to where the wake is going to be and how tight you essentially want the volumetric control to be around your car body and the wake. So now that you have your volumetric control, we can move on to meshing volume generation. So meshing discretizes the fluid volume into smaller cells for the simulation. So for external cars, trim cells and prism layer meshers are standard choices. The number of prism layers should be between 10 to 15 to yield higher accuracy external aerodynamic simulation. So this is best for solving boundary layer profile. For the prism layer total thickness, this is based on length of the car. So a good starting point is 1.5 to 3% of the car's length, and it ensures that the first layer is thick enough for the all Y plus wall treatment to work effectively. For the prism layer stretching, we want to set this to be 1.2. So this means that each layer will be 1.2 times thicker than the previous one. This essentially ensures a gradual transition to the core mesh. And next, you just want to run your mesh. So right click that automated mesh and select run mesh. And the run time for this took very low because it's a pretty simple model. But usually if it's more complex, if you have a more complex CAD geometry, CAD model, it's going to take longer. Next, we want to set up our reports. So reports are one of the core post-processing tools, and their main purpose is to extract quantitative numerical values from your simulation results. So it basically turns raw field data into useful engineering numbers. So a report calculates a single value or sometimes a small set of values by performing some kind of operation over a region, boundary, interface, derived part. And some common examples are force and moment reports, such as lift, drag, side force, pitching moment on a body, or mass flow rate through an inlet or outlet, average pressure, heat transfer rate, integral quantities like volume surface area, and balance check, such as mass imbalance, energy imbalance. So reports give you the numbers you typically write in the tables, put in your reports or presentation, or use to judge whether a design meets requirements, such as coefficient of drag is 0.312, or coolant mass flow is 1.8 kilograms per second. So after we run our mesh, we want to set up the reports for coefficient of drag and coefficient of lift, and we do this under reports, flow/energy, and then force coefficient. And we do this for each one, so coefficient of drag and coefficient of lift. And we want to use the subtracted surface when selecting its parts. So once we create that first report for our first coefficient, we want to go into that report, right click it, select edit, and then specify. Directions are basically where the forces are coming from. So in a car, lift is also referred to as downforce, basically what sucks the car into the ground. And we first want to specify what the parts we are working with are. So as I mentioned before, we always want to select that subtracted car part. So as mentioned, we can specify that direction. The reference density is going to be that air rho at sea level, so about 1.225 kilograms per meters cubed. The reference velocity is the inlet velocity, so 20 meters per second. The reference area is the frontal area, so the cross section from the front view. This is measured on the CAD model as we did before. We can then rename this to CD report or coefficient of drag report. This is because the direction, as we can see here, is coming from the X, so it's going to be that airflow that is hitting the front of the car. Next, instead of repeating the whole process for coefficient of lift, we can simply copy and paste the report for coefficient of drag. Rename it CL report, and then change the direction to be 0, 1, 0. Next, we're going to create the plots for these reports. So Sim Center STAR-CCM plots are visualization tools that graphically display data collected over time or iterations, and the main purpose is to help you see trends or convergence behavior, oscillations, transients, and overall solution progress or history at a glance, instead of just looking at raw numbers. They turn a time series data into easy-to-read lines, curves, or other chart types so you can quickly judge, is the solution converging, is it oscillating or cycling, how fast is it stabilizing, and are there any weird spikes, drops, and what's the final or current value looking like. So for a coefficient of drag and coefficient of lift plots, the lines start high or wobbly, and then they gradually flatten out and become horizontal. So you watch until the curve is flat enough, and that means that it converged. So your final value is what your report will give you. So to create that first plot for the first coefficient, you right-click the plots, select new plot, select monitor plot, and then rename the monitor plot to CD report monitor plot. Another simple way of creating monitor and plots for your reports would be to just right-click your report. So in this case, right-click that coefficient of drag report, and then select create monitor and plot from report. And do this for both coefficient of drag and coefficient of lift. Now you can initialize your solution and hit run. So initialize solution is that green flag, and run is the running man. So in a car external aerodynamic simulation, so in this case, the steady state RAN solver, typically for drag lift, like coefficient of drag and coefficient of lift, the residual plots tells you how well or how poorly the solver is actually solving the governing equations. So continuity, momentum, turbulence, and energy, if that's included. So across the entire domain. And these residuals measure the imbalance or the error left in each conservation equation after each iteration. So it shows them as normalized root mean square values per variable. So like per continuity, per x, y, and z velocity, k, omega, epsilon, etc. So lower residuals means smaller errors, and the equations are closer to being satisfied everywhere. And typically we'll see the residuals plot for a car aerodynamics case for continuity, which is the mass conservation. It's often the slowest to drop. Velocity component and the x, y, and z, these are momentum equations, and the turbulence quantities like k, omega, or epsilon are especially relevant for wake separation and drag predictions. For residuals, you can also specify the maximum plot samples, which controls how many data points, iterations, or time steps the software stores and displays in the residual history plot. So it essentially sets the maximum number of historical values kept in memory or plot for that monitor. And the default value is usually 5,000, but you can decide the value depending on the sim length and what you need to analyze. So for a shorter run, which is about 100 to say 2,000 iterations, the default 5,000 is usually fine. But if you're looking at more medium runs, which is about 5,000 to 20,000 iterations, you want to increase this to about 20,000 to 50,000. So you can see the full residual drop from the noisy early iterations through convergence. For longer or very long runs, 10,000 or 100,000 plus iterations, You want to set this to 100,000 or more than this. This essentially prevents the early important part of the residual history or initial drop from disappearing as the simulation keeps running. So as a general rule of thumb, set it at least as high as or a bit higher than the number of iterations or time steps you expect to need for convergence, plus some margin. So again, the lower the residual, the smaller the imbalance or the error in that equation, and the better the numerical solution satisfies the physics. For x, y, and z momentum, these are the three momentum equations, so Newton's second law for fluid. It's the rate of change of momentum or the forces. And they essentially measure how well the solver balances the convective pressure, viscous gravity, and other forces in each Cartesian direction. So the different directions can behave differently because of your flow or physics, and it might be anisotropic, which means just stronger gradients in z if there's buoyancy, gravity, or in x if it's the main flow direction. So if the residuals are good, low and flat, but the coefficient of drag and coefficient of lift drifts, you'll want to check your mesh quality, your reference values, or initialization. For a production car aero drag lift prediction, many teams accept residuals about 1 e to the negative 4 plateau and stable coefficients within about 1 count variation. So here I just left the coefficient plots running for a little bit longer, and these were essentially the final results. So as you can see, it was oscillating for a little bit in the start and then just started to stabilize into that horizontal plot that we are looking for. Next, if you look at that output section towards the bottom and you increase that real estate so that you can see all of the number, the iteration number, the continuity, the x, y, z momentum, and you're able to see the coefficients reports and what the final numbers are. So we can see that the coefficient of drag and the coefficient of lift were fairly small, about 0.22 and about 0.043, which tells us that the solution converged. Yay! I reran it a few times just to double check, but the solutions were pretty stable overall. I didn't realize that I stopped recording, but I created scenes, as you can see in the scenes subfolder. I created 3 specific scenes, but for now we're just going to cover the pressure scene to keep it simple. So to create a scene, you want to go to Scene, Create Scalar Scene, select Subtracted Car Surface to visualize the velocity, the pressure, or the stream. So if I'm going into my pressure scene, as you can see, I selected the subtracted car part, and I do this for the part section and for the region section. And these were essentially all my settings, which were the default settings. And then under scalar field, you can see that under function, I specified pressure coefficient, and the auto range is the min and the maximum values. You want to repeat this process for the other 2 scenes that you have. And then under the auto range color bar, I like to make the color bar blue-red. I feel like this makes all the colors much more clear and it's better for presentation and it shows your work very clearly. So as we can see here, when you click on the pressure scene, you can clearly see the pressure coefficient all throughout the car, and you can see that range of colors from very dark blue to dark red and the minimum and maximum value. So in this case, the minimum value is negative 3.95 and the maximum is 0.9. So if you scroll down and go to the field functions and check that pressure coefficient for your field function, you can see the reference density, the reference pressure, and the reference velocity that we specified earlier. You can do all these checks for all of the scenes, scalar values that you will use. So again, you have your reports, your monitors, and with those you can generate your plots. And then the last step would just be to get your scene. And this is the last step because you want to make sure that everything converges and your numbers are solid before you display anything and start interpreting this data more visually. So again, to create a new scene, you right-click Scenes, and then click New Scene, and then click Scalar to create that scalar scene. And voila, you have your initial results for your pressure coefficient. So this high pressure behavior in the front aligns well with physics principles. As we can see in the front of the car, we have those high positive coefficient of pressure values around 1, which is shown in red. And this is a classic stagnation behavior for oncoming flow, which slows to near zero velocity at the front. And it's converting kinetic energy to pressure. So for incompressible flow, which is typical in subsonic car aero, the theory essentially says max coefficient of pressure is about 1 at the stagnation point. So these results align really well with physics, as it's the high pressure right where the air hits the nose the hardest. And the roof, sides, and rear are mostly negative coefficient of pressure, which are yellow, green, and blue tones, all the way down to about -3 in certain spots. And these negative values indicate suction or low pressure zones from flow acceleration over curved surfaces. This is the Bernoulli effect, or separation or wake regions. The very low values are often seen in strong acceleration areas like roof curvature or separated flow. So this is one of the easiest qualitative checks in external aero CFD. And if the front didn't show strong positive coefficient of pressure, something would be wrong. So for example, bad reference values, wrong inlet setup, or flow just isn't impinging properly. So that's all for this initial beginner simple video. I hope you learned something, and thanks for watching.